In this video, I want to talk about exponential fitting and how one can use inverse Laplace transform to do that. So we are giving experimental data in some time bins. So we have time data and amplitudes, and we assume that these amplitudes are given by an exponential decay or a sum of exponential decays. So each of these exponential decays has a coefficient or an amplitude ci and a decay rate tau I, and the amplitude or the a at time point tn is approximately given by the sum of those exponential decays. And what we want to do is find the amplitudes or the coefficients ci and the decay rates tau. So for test data, we now use double exponential decay. So we have a function that takes two coefficients and two decay rates and outputs the sum of them, and we add a bit of noise. So we assume that our experimental data is somehow not fully accurately measured, but it's a little stretched or a little dampened by some log normally distributed. And the one basic thing that you can do is exponential fitting. So you fit your data with you give SciPy a function that takes in the amplitudes or the coefficients and the decay rates and outputs the function that you want, so the sum of the two exponential decays, or you can do overfitting with three exponentials. You input the data and some approximation to your coefficients and the decay rates, and you will get as an output the parameters, so decay rates and the coefficients. Another thing you can do is to observe that this sum of exponentials resembles a discrete Laplace transform. So discrete in that sense that we take the Laplace transform, which is an integral over some distribution of decay rates, and multiplied that with exponential decay with that decay rate, and we get as an output our function. So like not a sum of exponential decays, but an integral of exponential decays. And in our example, this h of s would be just given as a sum over scale delta functions. And on this GitHub link, you can check out, they implemented the inverse of that transformation in Python. So they take as input an approximation or a measurement. The closer, the more accurate this f is measured, the more accurate you will get out this h, of course. And it outputs this h of s. So in this case, you get a discrete set of values for s and then amplitudes. For those decay rates. And so I did this comparison for simple example with two decay rates. Yeah, one would be 2.5 and the other was 0.3 with both equal probability or equal coefficients. And we can see for the exponential fitting, actually for the double exponential fit, the data matches pretty accurate. And for the inverse Laplace transform, the smaller decay rate is matched pretty well, but the larger one isn't matched that good. So what you can do, you can play around with various different configurations, and what you see is that the smaller your decay rates are, the better your inverse Laplace transform works, and the less decay rates or the less exponential decays you have in your model, the better is the fit. So more decays means that the inverse Laplace transform is favored. But this is just a trend that I observed while playing around. You can do more rigorous research on that.